Alright guys, as part of the bell ringer, I wanted you to identify the coordinates of the vertex for the following absolute value graphs. So as we transition out of chapter 3 and into chapter 5, I'm legitimately crying. As we transitioned out of chapter 3 and into chapter 5, a lot of the concepts and core values of graphing absolute values from chapter 2, graphing absolute values from chapter 3, are all still playing a role in chapter 5. So it's important to be able to identify the vertex and write the equation for the absolute value. Those skill sets are going to be reapplied in chapter 5. Is everybody okay with that bell ringer? Would you like me to bring some clippers in tomorrow and fix it? That's like the one time I'll accept that. Okay, the vocab. There is some new key vocab for this unit. So one of the key words is quadratic. You're going to hear me say quadratic a lot. You're going to hear me say parabola a lot. A parabola is the shape of the graph of a quadratic. So a linear function's graph shape was a line. A quadratic function's graph shape is a parabola. Okay, and then a quadratic function. A quadratic function is any function that can be written in the form y equals ax squared plus bx plus c. That is what we call standard form. Vertex form is the form in which you write the quadratic where you can see the vertex, much like vertex form for an absolute value. The axis of symmetry in a quadratic is identical to the axis of symmetry from a quadratic. It is the line that cuts the graph in half. It goes through the h value of the vertex. No, the graph's for the next part. Is everybody okay with this page? Okay. So the graph in the next part is where I want you to graph this function. This is called the parent function. The parent function goes through 5 key points. Its vertex is 0, 0, so you're going to plot the point 0, 0. The axis of symmetry is the dashed line that cuts that graph in half. And then the parent function has a 5 key point summary. So your vertex is at 0, 0. And then when x is 1, y is 1. Now when x is 2, since y is equal to x squared, y is 4. Since any number squared is always positive, this graph gets divided in half through 0, 0. So the points for -1 and -2 are the same values as the points at 1 and 2. So -2 squared is also 4, and -1 squared is also 1. So the graph is split in half through 0, 0, and we match our points to the left and right. So on your graph, you should plot all 5 of those points. We call that the 5-point summary of the graph. When we make our tables, we actually only have to make our tables using 3 of the points, since the graph is quadratic about the vertex. When graphing, we like to follow these same simple steps. So you'll always plot the vertex. The vertex is h comma k. In this case, and for our day 1, our vertex is going to be 0, 0 for every problem. So for day 1, our vertex is 0, 0. We're going to find and plot 2 points to the right, and then use that to find and plot 2 points to the left. Then we're going to connect our points to get a nice smooth curve. So recall, I said for today, our vertex is 0, 0, because my h value and k values are 0. So we plot our vertex at 0, 0. That means my table starts with the point 0, 0. The x values on the table are going to be 0, 1, and 2 for all our problems tonight as well, because we have no shifts left or right as of right now. We also aren't shifting these graphs up and down. 1/2 represents the a value. So in order to finish our table, we're going to multiply f of x times a. And the f of x values are always going to be that 0, 1, and 4 from the previous table. So we have 0, 1, and 4. But then what we're going to do is multiply each of those by 1/2 to get my new y value. So I'm going to plot the point 0, 0, 1, 1/2. And since that graph goes to the right one and up 1/2, it's always going to go to the left one and up 1/2 as well. It goes to the right 2 and up 2. So it's also going to go to the left 2 and up 2. If you think about your perfect squares, they go 0, 1, 4. Perfect squares go 0, 1, 4. What's the next perfect square? Blank, 16, 25. Which number did I skip in the middle? What? 9. Yeah, it's 9. So x is 3. 3 squared is 9. So the x values squared are the y values. So if you wanted to get one more point, you could go to 3, and then it would be like 9 times 1/2, which is 4.5. So you could also plot to the right 3 and up 4.5, and then take that point to the left 3 as well. Ooh. And when you connect those points, does 1/2 stretch my graph or compress my graph? Compress. Excellent. It got wider than the original. Because you multiplied by 1/2, these values are wider. The 0, 1, 4, and 9, those would have been my original parent function points. So the original graph would have gone through this point here, and those points there, so you could tell the original graph would have been inside, thus making this graph compressed. Anybody want to guess what the domain of this graph is? So it's compressed. What's my domain? What do you know about when a graph has arrows on it? Yeah, it's all reals. It's going in infinite directions. How about the range? Are there any negative y values? No. Do the y's live down here? Are they in my table down there? That vertex represents the minimum of the graph. The vertex represents the minimum of the graph. That means the y values are going to be greater than or equal to 0. They're going to be greater than or equal to 0. So if you have an A value that is negative, we call this concave down, or it reflects across the x-axis. If an A value is negative, the graph is concave down, or reflects across the x-axis. So we talk about reflection. The reflection of an absolute value and the reflection of a quadratic are the same in their nature. They're going to open the graph in the opposite direction it's meant to open. So a quadratic is meant to open up. If it's reflected, my graph will open down. So if it is positive, or you're positive, then you open up like a smile. If you're negative, then your mouth opens down like a frown. I'm sure we can't see it, but Caleb's probably frowning today. Okay. And then the last thing we talk about is stretching and compressing. The A values for stretching and compressing a quadratic are identical to the A values for stretching and compressing an absolute value. So as I said, everything we learned in the past is coming back for Chapter 5. We're thinking about the same vocab. We're thinking about the same domains, the same max and min, and key pieces of information. So we have a little bit of time. What I want to do is potentially go over one more homework question with you. I already did number 1 with period 4. So how about I do number 2 with you? Just reiterating the key ideas of A, how the graph is changed, etc. So in number 2, there's 2 things you should notice. The A value is negative and a 3. So A equals negative 3 tells me 2 things. My graph is reflected and it's stretched. So my graph is going to be narrow and open down. So for today and our lesson, the x values are always going to be 0, 1, 2. Since there's no h and k, my y value is going to be affected by yeah. which is 0, 1, 4, multiplied by that a value, which is negative 3. Because the y value is x squared times a. So you're plugging 2 in, so 2 squared is 4 times that negative 3. So basically what I'm doing with having you do these x and y's is not have to plug into this equation every time. It's a pattern. So it will always be the perfect squares of x times a. Yes, exactly. So you could plug these numbers in. Just make sure if you plug in, you follow order of operations. That's the other reason I did this. A lot of times students want to take negative 3 times 2 and then square it. And they end up messing up the order of operations and getting iffy points that way as well. So I try to like not create formulas, but like have little like mini things that help. So you get 0, negative 3, and negative 12. So obviously negative 12 is going to be on my negative 10. I'm just going to kind of plot my 2 points down there. But you have 0, 0, 1, negative 3, which means if it goes to the right one, it also goes to the left one, and down 3. And then it goes to the right 2 and down 12. And to the left 2 and down 12. So I'm just kind of going to wing those 2 points down there. So my graph is everything I said. It's narrow, it's reflected. But again, you can see that the domain is always all reals. And the range is dependent upon the vertex is k value, which is this point right here. This time it's less than or equal to 0 because it's open down like a frown. I don't ask you to do domain and range for your homework. I just want you to tell me the a value, the words, and make the table and the graph. So you're doing the front and the back. The back, you don't even have to do that. The back, you're just filling in what is the vertex. So you only have 5 problems to do tables and tell me their transformations.